Good morning students. In the previous lessons on organic chemistry, you must have learnt a few basic concepts like what is a nucleophile, what are the nucleophilic substitution reactions in haloalkanes. As well in haloalkanes, halogen is more electronegative than carbon. Halogen carry the partial negative charge and carbon carry the partial positive charge. In the nucleophilic substitution reactions, a stronger nucleophile replaces a weaker nucleophile. During the chemical reactions, the old bonds break and the new bonds are formed. This carbon carrying halogen is alpha carbon, and this alpha carbon is tetrahedrally surrounded by 4 groups. In addition to these concepts, before starting with this lesson, you must know what is optical activity, that is D and L isomers, the structure and chemical reactivity of carbocations, and the concept of kinetics of chemical reactions. And in the present lesson, in these nucleophilic substitution reactions, we'll study about this bond breaking and bond formation, that is, we'll study about the mechanisms of nucleophilic substitution reactions. Now starting with an example of a simplest alkyl halide, that is methyl halide, in which alpha carbon is tetrahedrally surrounded by 4 groups, 3 H atoms, 1 halogen, and it is attacked upon by the nucleophile. This is the center of negative charge, partial negative charge on halogen, partial positive charge on carbon, and the nucleophilic attack on this carbon. Now in this case, the bond breaking and bond formation take place simultaneously. Carbon-halogen bond breaks and carbon-nucleophile bond is formed. And this bond breaking and bond formation take place simultaneously. Here carbon forming 3 sigma bonds with 3 H atoms. Here we show the bond breaking with halogen and bond formation with the incoming nucleophile. This is bond formation with incoming nucleophile and bond breaking with the leaving group, that is halogen in this case. And as here the bond breaking and bond formation is simultaneous, this bond breaking and bond formation has to be from the opposite side only. It cannot be from the same side. The situation is similar to, let's consider a cinema hall in which there are 2 gates. One is for the entry and the other is meant for the exit gate. And let's consider a situation in which the time at which one of the show ends, at the same time the second show starts. So that the entry and exit of the viewers has to take place simultaneously. And during that simultaneous entry and exit of the viewers, it cannot be from the same gate. From the same gate, as it will lead to stampede. It has to be from the opposite sides only. So in this case, this is the incoming nucleophile, the entry point, and the leaving group, that is the exit point. The entry and exit, it cannot be from the same side. The entry and exit gates, they have to be on the opposite side, so the nucleophile has to attack from the other side. This is the correct representation and this is the wrong representation. If this is the frontal side, that is the side from where the leaving group leaves, then this is the rear side. If the leaving group is leaving from the frontal side, then the nucleophilic attack has to be from the rear side. It can be represented like this, the arrow pointing from the rear side, or what else can we do? Write the nucleophile on the left side and show the nucleophilic attack from this side. This is the correct representation, this is also correct, but this is the wrong representation. Now the entry and exit, that is the incoming nucleophile, bond formation, and the leaving group, that is a bond breaking. And this is our transition state in which the central carbon atom is surrounded by 5 groups. The point to be noted here is it is surrounded by the 5 groups, not the 5 bonds. This is the half bond, this is the half bond. Carbon can never form 5 bonds. Although these groups are 5, but bonds are not 5. And this transition state is a very short-lived, it cannot be isolated, so it is put into a square bracket which represents that this is highly unstable. Now when this bond formation and bond breaking is complete, then the substituted product is formed, and in that substituted product, this incoming nucleophile will occupy the position which is opposite to that of the leaving group. As here the leaving group is on the right side, the incoming nucleophile will occupy the position on the left side, that is it will occupy the mirror image position to the leaving group. This side the nucleophile, hydrogen on the left side, and we'll write here hydrogen on the right side. And so if this alkyl halide is optically active alkyl halide means in which all the 4 groups are different. As here we take 1 halogen, 1 hydrogen, 1 CH3, another is C2H5. This is optically active halide, partial negative charge on halogen, partial positive on carbon, and this compound is 2-halobutane. In this optically active halide, the nucleophilic attack on this carbon, again it has to be from the opposite side, not from the same side. If this is the frontal side, then the nucleophilic attack from the rear side, again a 5-membered transition state will be formed, and the nucleophile will occupy the position which is the mirror image position to this leaving group. Now let's consider a tetrahedral structure. In my fist is the central carbon atom, which is tetrahedrally surrounded by 4 groups. Here is a tetrahedral structure in which the central carbon atom in my fist is tetrahedrally surrounded by 4 groups. Suppose these are the 3 H atoms. This is the halogen, the leaving group, the incoming nucleophile, and as these groups are the smaller groups, the incoming nucleophile can attack from the opposite side, and there will be simultaneous bond formation and bond breaking. This is the leaving group, that is halogen atom. This is the incoming nucleophile which attack on this central carbon atom, alpha carbon atom, that carry the positive charge, and there is a simultaneous bond formation and bond breaking. A 5-membered transition state is formed. Here the central carbon atom which is surrounded by 3 H atoms, the incoming nucleophile, that is bond formation, the leaving group, that is a bond breaking, and in this 5-membered transition state, when the bond formation and bond breaking is complete, here the leaving group leaves and the incoming nucleophile occupy the position which is a mirror image position to this leaving group. Leaving group was on this side, and the incoming nucleophile occupy the mirror image position. And so, if this alkyl halide is optically active, then this will lead to the inversion of configuration. That is, if this is the D isomer, then the incoming group is on the opposite side, on the mirror image side. So this will be the L isomer. If we start with the L isomer, the product will be in the D configuration. That is, it leads to inversion of configuration. So here, the nucleophilic attack from the rear side, the simultaneous bond formation and bond breaking. One hydrogen, another is methyl. The third group is C2H5 ethyl. bond breaking with halogen, bond formation with the incoming nucleophile, a 5-membered transition state is formed. And when this bond formation and bond breaking is complete, now this is again a tetrahedral structure, the final product, which is a tetrahedral structure. So in this case, the CH3 group is written on the left side and in the product will write CH3 on the right side. The incoming nucleophile on the left side as the leaving group was on the right side. So incoming nucleophile on this side, here we have C2H5 and H. And as this is the optically active halide, this product is with the inversion of configuration. And this inversion, this is also known as Walden inversion. Then in this case, as it is a single step process, this is a one-step process in which the simultaneous bond formation and bond breaking take place. The rate of the reaction, it depends upon both the species. Both the species here means one is alkyl halide, another is nucleophile, and as it is a one-step process, the rate of the reaction which depends upon both the species, that is alkyl halide and the nucleophile, the order of the reaction is 2. As in this case, the rate of the reaction, it is dependent on alkyl halide and nucleophile both. The order is 2, or we say this is a bimolecular reaction. And this type of a reaction in which the simultaneous bond formation and bond breaking take place, this type of a reaction mechanism, it is SN2 mechanism, where S is for substitution, N is for the nucleophile, that is one nucleophile replaces another nucleophile, and 2 here means the bimolecular reaction, that is order is 2. So this is SN2 reaction mechanism, which is a one-step process in which the simultaneous bond formation and bond breaking take place, and the order is 2, or it is a bimolecular reaction. And if we go for the order of reactivity of different alkyl halides in SN2 mechanism, then as here the simultaneous bond formation and bond breaking take place, and carbon is surrounded by 5 groups. If these groups, they become more and more bulky, hydrogen is replaced with methyl, or it is replaced with methyl, second hydrogen is also replaced. As these groups become more and more bulky, the transition state become more and more unstable. So larger these groups, less the reactivity towards SN2 mechanism. So the simplest alkyl halide, that is methyl halide, is most reactive. When one of the hydrogen is replaced with R group, that is RCH2X, this is primary alkyl halide, is less reactive. The second hydrogen is also replaced with R group, that is R2CHX, the secondary alkyl halide. The reactivity decreases, and then when the third hydrogen is also replaced with alkyl group, that is R3CX, tertiary alkyl halide, that is least reactive towards SN2 mechanism. As here in SN2 mechanism, a 5-membered transition state is formed. More bulky these groups, less the reactivity. As the number of R groups that increases, the reactivity decreases. This is for SN2 mechanism. Again I repeat, which is a one-step process, simultaneous bond formation and bond breaking. The rate of the reaction depends upon both alkyl halide and nucleophile. That is, the order is 2. It is a bimolecular reaction. Now the second case is, as where with increase in the size of the R groups or with increase in the number of R groups, the reactivity towards SN2 mechanism that decreases. In that case, instead of the simultaneous bond formation and bond breaking, the reaction will take place in two steps. First, the bond will break, and in the second step, the bond will be formed. Now let's consider a second situation of a cinema hall. When there is overcrowding. In case of overcrowding, the simultaneous entry and exit that become difficult. And when there is overcrowding, first there must be the exit followed by the entry. So if there is overcrowding and one show ends, after some time the second show will start. First of all, the exit will be there. The hall will be vacated. Now, when the hall is vacated and also there is overcrowding, in that situation, both the gates can be opened for the entry point. Otherwise, one gate is meant for the entry and the other gate is meant for exit. But if there is overcrowding and the hall has already been vacated, then both the gates, they can be opened for the entry point, and there will be 50% entry from the front side and 50% entry from the rear side. That is 50% entry from the gate which is used for the entry and 50% entry from the gate which is used for exit. So let's consider another case. Alpha carbon. One bond is with halogen, partial negative charge on halogen and partial positive on carbon. And 3 R groups are there, CH3, CH3, CH3. That is, it is a tertiary halide, this is tertiary butyl halide, which is attacked upon by the nucleophile. Now, as these 3 groups are bulky, the simultaneous bond formation and bond breaking is not feasible. There is overcrowding. As here we can see, the 3 bulky R groups around the central atom. In my fist is the central atom, which is tetrahedrally surrounded by 4 groups. These are the 3 bulky R groups. This is the leaving group. And the incoming nucleophile cannot approach this alpha carbon carrying the positive charge due to steric hindrance by these bulky groups. The simultaneous bond formation and bond breaking is not feasible in this case. So what happens? First, the hall is vacated. The leaving group leaves. The viewers who have to leave, they leave. And when the leaving group leaves, this carbon-halogen bond breaks. Bond breaking in the first step. So when this bond breaks, then the carbon will be surrounded with these 3 groups only. And when this carbon, the central carbon, which is in my fist, is surrounded by 3 groups, this carry the positive charge. The hybridization in this case is sp2 and it has a triangular planar structure. The step 1 in which bond breaking takes place. Alkyl halide, alpha carbon tetrahedrally surrounded by 4 groups, halogen being more electronegative. This carbon halogen bond breaks, and when this bond breaks, this carbon is now left with 3 methyl groups. This carry the positive charge. This is sp2 carbon, the central carbon is sp2 carbon, and this is a triangular planar structure. This is carbocation intermediate. This step 1, that is bond breaking, is a slow rate determining step and is reversible also. So here the carbon halogen bond breaks. This leads to the formation of an intermediate. This intermediate is a triangular planar species. The hall is now got vacated. The leaving group has left. Now this is the situation. Here the carbon is surrounded by 3 groups. It forms a triangular planar structure. Now the nucleophilic attack. It can be with 50% probability from the frontal side. Frontal side means the side from where the leaving group has left. And the 50% probability is from the rear side. Rear side means from the opposite side. So 50% probability for the frontal attack and 50% probability for the rear attack. If there is frontal attack, then the incoming nucleophile will occupy the same position which was occupied by the leaving group. As leaving group was on this side and the incoming nucleophile that also occupy the position on this side if it is a frontal attack with 50% probability. And at the same time, there is 50% probability for the rear attack. And when the rear attack takes place, then the situation is like this. And in this case, the incoming nucleophile occupy the position which is the mirror image position of the leaving group. The leaving group was on this side and the incoming nucleophile is on this side. In this case, the incoming nucleophile occupy the mirror image position. So if there is frontal attack with 50% probability and if this alkyl halide is optically active, then this will lead to the retention of configuration, and if there is 50% attack from the rear side and also this optically active halide is there, then this will give the 50% of the product with the inversion of configuration. If the incoming nucleophile is on the same side, this leads to the retention of configuration, and if it is on the opposite side, then it leads to the inversion of configuration. As here, the triangular planar species, and in the second step, the nucleophilic attack takes place with 50% probability from the frontal side and the 50% probability from the rear side. This is step 2, which involves bond formation. And when this bond is formed, this is a fast step and it does not affect the rate of the reaction. This is the slow rate determining the step 1. The step 2 is a fast step which does not affect the rate of the reaction, and the nucleophile with 50% probability occupying the same position and with 50% probability occupying the mirror image position. So if nucleophile on this side, then we have 3 groups here and 3 groups here. In this case, the compound is not optically active. So there is no difference in these two. The two are identical. There is no difference. The difference will arise if this compound is optically active. Now let's consider the optically active compound for the same reaction. One hydrogen, second ethyl, third is ethyl. Partial negative and partial positive charge, partial negative on halogen and partial positive on carbon. Step 1 is bond breaking, and this step is a slow rate determining step where the carbon halogen bond breaks. This leads to the formation of a carbocation intermediate. This carbon carry the positive charge. This is sp2 hybrid and is a triangular planar structure, the first step, that is the bond breaking. Then bond formation takes place in the second step. Step 2, that is bond formation, which starts with this intermediate and nucleophilic attack with 50% probability from the frontal side. This step is a fast step which does not affect the rate of the reaction. There is 50% probability for the frontal attack, that is nucleophile will attack from the same side from where the leaving group leaves. And in that case, the nucleophile will occupy the same position which is occupied by the leaving group. Hydrogen, methyl and ethyl. 50% product, and this is with the retention of configuration. And there is 50% probability for the rear attack. The nucleophilic attack on this carbon carrying positive charge on the carbonatile intermediate, where 50% probability from the rear side, and when there is 50% attack from the rear side, then the nucleophile will occupy the position which is mirror image position to the leaving group. As in this case, the leaving group is leaving from the right side. The nucleophile will occupy the position on the left side. And as here, the nucleophile is on the opposite side, this leads to inversion of configuration. So 50% of the product is obtained by the retention of configuration and 50% of the product is obtained by the inversion of configuration. If we start with deconfiguration of haloalkane, then this product with retention of configuration is in the deconfiguration, and this with the inversion of configuration is in the L configuration, or vice versa. If this is in the L configuration, then retention product is in the L configuration and inversion product is in the D configuration. And in either case, we will get 1:1 mixture of D and L isomers. And this 1:1 mixture of D and L isomers, that is 2 enantiomers, this mixture is called a racemic mixture. And in this racemic mixture, the specific angle of rotation is 0, as the 50% of D isomer will rotate the plane of polarized light towards right, and 50% of L isomer will rotate the plane of polarized light towards left. So net specific angle of rotation for a racemic mixture is 0, although both the components are optically active. And in this case, as this is the slow rate determining step, in this slow rate determining step, the rate of a reaction, it depends only upon the concentration of alkyl halide. Nucleophile appear in the second step. Second step is a fast step which does not affect the rate of the reaction. So rate of reaction does not depend upon the concentration of nucleophile. Rate of reaction depends only on the concentration of alkyl halide. And so the order of this reaction is 1. This is a two-step process, and this two-step process in which order is 1, this type of reaction mechanism is SN1 mechanism. S for substitution, N for nucleophilic, in which one nucleophile replaces another nucleophile, and 1 here means unimolecular. Unimolecular means order of the reaction is 1. So SN1, which is a two-step process, it is a unimolecular reaction in which the rate of reaction depends only on the molar concentration of and in the two steps, the step 1 is the bond breaking and step 2 is the bond formation. And product formed for the optically active compounds is with 50% retention and 50% inversion, and that leads to the formation of a racemic mixture. So here in alkyl halides, they can react either by SN1 mechanism or by SN2 mechanism. SN1 is a two-step process and SN2 is a one-step process. In this case, first step bond breaking and then bond formation, and in this case, the simultaneous bond formation and bond breaking. In this case, with increase in the bulkiness of the groups, the reactivity that increases because the stability of the carbocation intermediate that increases. So, tertiary group is most reactive, then secondary, then primary, whereas in this case the order of reactivity is reversed. As the bulkiness of the groups increases, the reactivity decreases. And alkyl halides, they can react either through SN1 mechanism or through SN2 mechanism depending upon the bulkiness of the R group which is attached to the alpha carbon atom. Hopefully you have understood the SN1 and SN2 mechanisms, and now you must be able to answer a few questions on this basis, like the order of reactivity of the different types of alkyl halides in SN1 mechanism or in SN2 mechanism. You must now be able to compare and contrast SN1 and SN2 mechanisms, and your home task is go through the examples 6, 7 and 8 from NCERT Unit 10, and also the back exercise question number 9 and 15. Thank you so much.